advanced research in anti-gravity fields, free energy, psionics, fascinating new field. And we'll be discussing those factors with you today and presenting a working model of an ionic propulsion anti-gravity system. And with that, I'll throw it over to Rick Todish.
All right, hello. I'd like to start out talking about Future Horizons a little bit. We do a lot of high-tech electronics manufacturing. We sell a lot of fringe science type information. And we make it an effort to try and verify a lot of that information as much as possible. Whenever possible, we try to produce working devices and actually sell them to the public. Some of the topics we deal with are free energy, anti-gravity. We do some real far-out stuff, some theoretical time travel stuff, space-age weapons technology, some new non-lethal weapons, lasers, ultrasonics, a lot of real modern, high-tech concepts. We have a catalog that we currently ship all over the world. We sell, I think there's something like 120 different items in the catalog at this point. And it's gone real good. I started the company about 1.5 years ago, and it's been an explosive growth, and I've just been holding on to the tailcoats of the company, and it's been going real good. We try to take as much of the profits from the various plans and assembled units that we sell, and we try to sink them back into more research. I don't like the idea of wasting my time or money on a patent. My attitude is just get it out there. Let's change the world with this technology. Currently, we've got 4 regular employees. I've actually got a lab in Michigan. We do the manufacturing of all these devices in-house. We've got a number of engineers that do a lot of the design work for us on some of the more complex stuff. And most of them work as contractors or consultants. And a lot of them are close friends of mine. And we've set up a pretty good system where we can exchange technology between ourselves and keep the costs down for everybody. So it's worked out real well. Some of the projects that we're working on right now, just to give you an idea of some of the far-out devices that we do work on, we're currently working on a cloaking device. Anybody familiar with Star Trek out there? Cloaking device is a gadget that renders an object invisible through the bending of light. And you'd be surprised how simple that technology really is. We're working on an application to create a suit that'll actually act as electronic camouflage and render the user virtually invisible from about 100 yards away. So that's one of the far-out things that we're working on. We also deal with some holography. We're working on a holographic projector, free energy devices. I'm trying desperately to get our free energy prototype ready for sale. We're close, and we're trying to keep the costs down, and it'll be a real basic design just to verify the concepts of it. Of course, the Ion Propulsion has been one of the bigger things. The website address is www.futurehorizons.net. That's how I started the company originally. The website, I think we're up to about 700 or 800 hits a day now, so it's gone real well. We have ads running in about 5 or 6 magazines in the United States, Europe, and Australia. So as the money keeps coming in, we'll keep the technology pouring out. So, I'm here to talk today about the Ionocraft. It's an ion propulsion device that we've been working on for quite some time. You might ask, well, what is an Ionocraft? What is ion propulsion? Ion propulsion is a device where you can convert electricity directly into thrust through this device. It's been around for quite a while. It's a real simple technology. We can do some really incredible things with it on more advanced models. The technology was invented back in the 1960s by a gentleman named Major D. Zversky, and he's actually got a patent on it, patented in 1964. he actually got the idea from, he was the inventor of the electronic air cleaners. It's a device that uses electricity to actually cause a flow of air through the inlet out to the outlet. And it'll take the air and actually trap the dust particles electrically. There's no moving parts, but yet there's a breeze coming out of this device. And he realized, well, if anything can create a thrust, it's got to be able to fly, given the right adjustments to it. Also, another patent done in 1964, right around the same time that Seversky got his patent. It was done by a man named Hagen. And he's actually got a very similar device, works on the same principles, just different geometry. And that's really been the groundwork for most of my research, and I've tried to use it as sort of a stepping stone into this, some newer developments. This is a picture of
hit C.
well, let me just go. Okay, here we go. This is Major D. Seversky with his Ionocraft. This is, to my knowledge, the largest device that he actually built. It's a 3-foot square device, very lightweight. It's basically balsa wooded and aluminum wire, real flimsy, real weak, but it effectively demonstrated the principles of ion propulsion. I've actually seen this device in flight. There's been a couple of videos made. I wish I didn't have time to put them together for this presentation, but it's a pretty interesting device. Here's another picture of it, actually in flight. It obviously doesn't carry its own power source. It's tethered to umbilicals to a high voltage generator that actually power the craft. Here's another picture. He's using a device to inject smoke underneath the craft to denote the contrails from the ion wind that's generated underneath the craft. Okay, let's look at the basics of ion propulsion. What is it and how does it work? It's actually, like I said, very simple. It uses two grids of wire separated by a fixed distance. A charge is applied to these grids. A positive and negative charge would go to each grid. When you apply the charge to these grids, you actually get a flow of air in between the grids. And the way that actually happens is similar to a high voltage device. Anyone familiar with high voltage, you'll notice a couple 100,000 volts or 20 kilovolts. If you've got a sharp point on the high voltage output, you can get ions to jump off of that point, such as like a needle. The ions basically are jumping off of the upper grid, being attracted to the lower grid. What happens is they interact with the air molecules in between these two grids, and the ions are shot downward. The upper grid emits the ions to the lower grid. The ions are sucked into the lower grid, but the air molecules are attached to these ions as they're in flight. And so the air molecules actually are thrust downward through this grid. If you put your hand underneath the device as it's operating, there's actually a small breeze blowing. So it's real simple. The power source for these craft typically are high voltage power sources. In theory, you could really use almost any potentials, but I found that 20,000 volts DC seems to work real well. In fact, the generator that I've got here right now, that's about a 20,000 volt generator. It's about a 1 milliamp output. So it doesn't take much to get them to fly. One of the important points on the theory of ion propulsion is symmetry. In this picture here, you'll notice I've got the two square grids. There it is, okay. The two square grids are actually identical, and they're placed above each other. The problem is symmetry is not a good thing in ion propulsion. You want them to be asymmetrical. You want the upper grid to be different than the lower grid. The reason is, if they're the same as in this picture, what you get is losses where the ions will actually travel to the path of least resistance, which is every one of these wires placed right above the other wire cause these losses to occur. So that might sound a little confusing, but this should clarify it a little bit. This is the improved design. This uses the emitter wires in a diagonal pattern. Now, the diagonal pattern makes a major difference in thrust. The reason is, when the ions are emitted from this diagonal wire, they don't have as direct of a path to ground, to the lower grid. So they tend to interact with a larger volume of air surrounding the emitters. And obviously, the name of the game is to get that air to interact with these ions so it'll be thrust downward more effectively. Okay, one of the other important things you'll notice, well, in this drawing here, these emitter wires, they're actually smaller than the lower grid wires. The lower grid wires, increasing the size or the diameter of those wires tends to increase the thrust, but it doesn't necessarily increase it enough to warrant using bigger size wires. So we've typically used about 10 mil wire for the lower grid. The upper wires, we've found that 2.5 mil wire works the best. And that was actually determined by the patents. That was my starting point to experiment with. And I have tried a number of different size wires, and the 2.5 mil is definitely the best at producing the effect. We've tried a number of different wire types. Well, we started out with aluminum wire. That was probably a mistake. Aluminum wire at 2.5 mils is finer than a human hair, so you can imagine how easy it breaks. So we've switched to stainless steel wire. It's about 100 times stronger. Unfortunately, stainless steel is springy, so when you try and work with it, wrap it around these balsa wood struts, it tends to unravel, and so you've got to glue every wire. It's definitely a tedious job, and it's tedious work. The other thing that seems to affect it quite a bit is using this small diameter wire. The wire is able to vibrate, actually, as it produces this effect, and that's an important point. We've tried using bigger diameter wires for the emitters, and it doesn't produce enough thrust. With the smaller diameter wires, you get a vibration that occurs, sort of like a piano wire. And the vibration tends to rattle loose those ions that are stuck in that wire. And it does drastically increase the thrust. The other point of importance, probably one of the most important points, is the grid distance, the distance between the upper ion emitters and the lower grid. And it's a real tricky thing to get that exactly right. There'll be a point, if the grids are too close together, you'll just strike an arc of electricity between them. That's not a good thing. Every time an arc is struck, you're losing power because the ions are being sent straight to ground. So the trick is to move them the correct distance away. Typically for this demo, this generator is 20,000 volts, and it's about 1.75 inch separation. And that tends to work the best. One of the easiest ways to actually determine that, for any of you that may experiment with it, is if you've got a variable high voltage power supply. The easy way is to just build the device, maybe 1.5 inch or 2 inch separation, and turn up the dial of the power supply. There will be a point where you'll achieve maximum thrust for the device, and if you go past that point, you'll actually start losing thrust, and if you go too high, you'll obviously strike an arc and it won't fly. The name of the game in this, one of the tricks that was determined by a lot of the researchers that have worked with this, is that the device is most efficient and tends to work best when the ions are at a low velocity. The air output of this device is less than 10 miles per hour, the air actually being ejected from the bottom of the craft. And that's important because higher speeds of these ions creates an effect known as secondary ionization. And that tends to cancel out these ions that are hitting the lower grid. And every time you cancel out an ion, you're just decreasing your thrust. So the trick is to get low velocity airflow with moving as high of a volume of air as possible. And I'll talk about that in a few minutes here. Okay, let's look at the picture again. One of the problems that we had at the beginning was how do we scale this device up? The prototype here is only 8 inches square, and our original idea was, well, let's just build a 12-inch or a 14-inch device exactly the same, and let's see what happens. If you look at the picture here, imagine now this device being maybe 12 or 14 inches across, and all of the areas directly underneath the emitter wires are the areas that are being used on the lower grid to contribute towards thrust. On a bigger device, you can see there's a large amount of wasted area that the ions aren't going to reach. And so that was a problem. If it's not being used for thrust, it's dead weight. And dead weight is not a good thing. So what we found, came up with somewhat of a solution to that, and that was to link multiple craft together. The trick was to get as many of these X's as possible into a small space. Doing it that way, we get good coverage of the ions on the lower grid. That's really the important thing, because we want every square inch of that lower grid being used to contribute towards the thrust. Otherwise, like I said, it's dead weight. And that's what this, we've done some experimenting with this craft here that you see, and it seemed to work, and it seemed to greatly enhance the lift of the craft. Okay, the real trick in this is to increase the density of these emitter wires as high as we can possibly get it. There's definitely some problems with the technology that we're still working out, but the higher the density of these emitter wires that we can get without causing symmetry or cancellation of these ions, it will allow us to greatly increase the thrust on, say, a 1 foot square device. We have come up with a number of improved methods to increase the emitter density on this device, and we're still experimenting with it, and it's still in prototype stage, so I don't really have anything to show with that yet. But the larger these craft get, the more thrust they produce, and it's pretty interesting. As you start scaling this device up, your efficiency greatly goes up, and you get a more efficient device, and you don't get as much secondary ionization. Also, you know, in a small device, this, as an example, the small device we've got here on the front of the box, that device weighs 0.2 ounces, and it produces 0.3 ounces of thrust, so it's got a net thrust of 0.1 ounces. Now, that might not seem like much, and you're probably thinking, well, big deal, what can we use this for? But when we start combining multiple craft together, that 0.1 ounce is a significant amount of thrust in a larger craft. You could easily envision a craft maybe 10 or 20 feet in diameter that would be capable of lifting a substantial payload. This is a picture of our friends at NASA. Their Deep Space One probe. Some of you may have heard of this. Surprisingly, it wasn't very well known on the news. A lot of people have never heard of it. But NASA launched this probe on October 21st of 1998, October 24th, excuse me. And this was the first experimental space probe to ever be launched that used an ion propulsion engine. It's an amazing device. It was launched primarily with the mission to explore some new technologies that NASA had been working on, such as the ion engine. I'll get to that. That's a good point. Oh. Here's another picture of the ion engine. Let me see if I can zoom that up. 17.5 or 0.6 pounds. Now, if you look at the thrust on this device, 0.02 pounds, 90 millinewtons. And you're probably thinking, wow, what the heck could they possibly do with 90 millinewtons? 90 millinewtons is about the equivalent thrust of resting a piece of paper on your hand. That's how much thrust that this device actually produces. But believe it or not, in space, you don't have wind resistance. It doesn't take much to quickly accelerate this craft to high speeds. For instance, on initial startup, you're in the first couple of seconds of flight, you're going at a fixed speed. 10 seconds into the flight, you just doubled your speed. So it's constantly doubling its speed. If you look at the top speed of this device, it's 68,000 miles per hour. It takes it about a month to 2 months to achieve that speed. So it's got some real incredible futures ahead of it. They're looking at using it for a possible manned mission to Mars. And to do that with a rocket, it cannot be done. You'd need a large capacity of fuel to be able to produce that same effect. So it's much more efficient. This is another picture of one of the test beds that they use for the Ion Propulsion engine at NASA. This is a picture of the thrust coming out of the Ion engine, and it's in a dark room, and you can see that there's a contrail illuminated through the Ion thrust. Here's another picture of it. Okay, this is a design schematic of the Ion engine that NASA created. It's real simple. It's very similar to our device. You've got an emitter that emits these ions inside of the engine, and they've got magnetic rings around it to contain the flow of ions better so that you get a more direct output thrust. Now, the output of the device right around here is an accelerator grid. They can actually accelerate the speed of these ions drastically. And NASA's sort of going about this in a different way than we are. They're trying to produce the fastest ion that they can possibly eject from this craft. And our goal is not to do that. We're trying to keep the speed of the ions slow. The reason they do that is without that high-speed ion, they wouldn't be able to achieve these faster speeds. So they're going for a higher energy ion beam on the output. Okay, one of the most important points about NASA's space probe is an interesting one. Ion propulsion does not work in space. So they actually came up with a very interesting solution to that. The reason it doesn't work in space is you need air or atmosphere or some type of a gas for these ions to actually interact with as they travel between the grids. And they found that xenon gas works the best, and that's actually a very interesting choice. Xenon is about 4.5 times heavier than air. So it's sort of equivalent. It's kind of like thinking of a baseball pitcher throwing a fastball at 90 miles an hour. That would be the equivalent to an ion propulsion craft in our atmosphere. Using xenon gas as the gas, it would be similar to that same pitcher throwing a shot put at 90 miles per hour. The atoms there's much more momentum being created as they're thrust out the bottom of the craft. Okay, some of the things that we spent a lot of time with was trying to verify a lot of the points in the patents, whether they were valid or not. As many of you know, it's easy to get a patent. It's difficult to get a patent that actually produces a working device. You'd be surprised at how many patents there actually are that have devices being described that don't actually work. So we spent a lot of time trying to verify this information. And we've tried to take a lot of the suggestions of the inventors of the patents and tried to work with them. One of the improvements mentioned in one of the Hagen patent was to use fabric strips in between the ion emitters. Now, I won't really go into too much depth about this, just to say that this is the top view of the craft right here. And instead of running the emitters diagonally, he ran them parallel, straight up and down. And he discovered that fabric strips being placed in between the ion emitters tended to cause less interference between the adjacent ion emitters, and that improved the flight. Unfortunately, I've done this experiment many times, and he's right, the fabric strips help, but the added weight does not make up for the improvement, so in my opinion, it's not a very good idea. This same craft, he used, if you see, there's an outer ring and an inner ring on this craft to actually hold everything together. He used eighth-inch aluminum tubing. Well, I find it hard to believe that that device flew with eighth-inch aluminum tubing. You know, one piece of that stuff is 3-4 times the weight of my entire craft. He decided in the patent that it was a good idea to cut this tubing in half and have the sharp edges of the tubing facing down to eliminate some of the secondary ionization. And I've done that experiment too, and yes, it does eliminate secondary ionization, but it doesn't make up for the added weight. So it's another thing that really didn't work. One of the other things that was suggested in the Seversky patent was to use strips of foil underneath the collector grids. The strips of foil tend to allow better attraction of the ions down to the lower grid. And that does seem to work, and it actually more than makes up for its own weight. Unfortunately, it's so fragile, we didn't really want to put it on this prototype to show. Just by touching it, it's aluminum foil, so it's kind of a nightmare. One of the other things that was suggested in both patents, and I've found it to be one of the key factors, is stacking these grids on top of each other. It's very easy to just design one layer, and then by putting a second identical device on top of that, you're able to accelerate the flow of these ions without causing these losses. So in theory, you could get airflow coming out the bottom of this. You could build one 20 feet high and get very high flows of air coming out the bottom of the device. And that's actually an important thing to remember when I start talking about the larger craft that we're working on. Potential uses of the device, you're probably wondering, and you're probably looking at this prototype thinking, what the heck could we possibly use it for? It actually has a lot of potential uses. If it's built correctly, we could use it for remote piloted vehicles, for reconnaissance. We could build ultra-high flying communications platforms. In theory, these devices can fly so high where fixed-wing aircraft couldn't fly. It may be possible to achieve low Earth orbits with some of these devices where they just continually fly around. One of the other things that I've been looking into for a number of years is the possibility of a manned craft. And based on the numbers that I've seen, I think it definitely is possible. There are some problems to be overcome with it. Structure is the number one problem, trying to distribute weight on such a lightweight craft. Some of the benefits of the technology. A lot of the benefits might be obvious, some of them might not. Vertical takeoff and landing. We can take off like a helicopter, land like a helicopter. We can fly higher than any aircraft. The projected flight ceiling of this device is about 300,000 feet, which is incredible. We're able to convert electricity directly into usable thrust, which is a very efficient conversion. It's noiseless. It doesn't make any sound as it flies. The small prototype does spark a little bit, but on bigger craft, it's just a small breeze that blows, so it's a quiet device. There's no moving parts. There's no wear and tear. The maintenance is minimum. It's a very simple device. And given the correct configuration, high speeds are definitely achievable with it. Okay, some of the future goals that we're trying to accomplish with this technology is a lot of research. We need more research, and we need to do more to figure out better ways to improve the device. We're working on a 3-foot craft that's a balsa wood constructed craft, and it's 3 feet triangular shaped. Our goal with that device is to come up with a good, solid, rigid structure that we can use as a frame network to actually create this effect on top of. The prototypes that we've got now are very fragile, flimsy, they flex, and that's not a good thing. If we're ever going to get to the point where we can use this device for any useful application, we need a rigid airframe. So the 3-foot craft that we're working on will hopefully solve those problems, and we'll be incorporating some of our new designs into that device. The next step from that, the most logical step, is to achieve flight control. We're looking at a 6-foot device from there, the same configuration, triangular. And we hope to be able to balance the device. When they fly, they're erratic, they're unstable, and they're unpredictable. And we really aren't able to correct that on small craft like this. There's just simply not enough thrust to really do anything with. So the 6-foot craft is our goal to be able to solve those problems. And that'll allow us stability. We'll be able to take off and land with a real stable flight. We'll be able to steer it, tilt it, bank it. The next craft above that is really our major goal, and it's a 12-foot craft. Let me show you a picture of that. This This is a real primitive picture, but kind of gives you the idea of what we have in mind. It's basically 12 feet across. The Ion engine composes most of the craft, and it'll have to be built very lightweight, probably out of balsa wood. We have used carbon fiber in the past on some of these airframes, but until you get to bigger craft, it's not really a very well, it's not very good trade-off. We use the delta wing airfoil for this craft. Typically, delta wings are normally used in high-speed aircraft, but because of there's some enhancements with delta wings that improve the lifting factor of airframes, and that's why we chose this for the Ion wing. The air intake would be right in the top of the Ion engine, and it would flow out through the bottom. If you look at the lower picture there, the lower thrust louvers, these louvers are basically the same as louvers on your window. They'll be controlled electronically. They're shutters. And by pointing those on takeoff straight down, the airflow will be projected straight down underneath the craft. As we get up off the ground, we can tilt these louvers to the rear and direct as much thrust as we need to the rear of the craft. Now the craft shoots off in a horizontal direction, and we're actually using the airfoil itself for added lift. So it flies typically like a conventional aircraft, but it's got the bonus of no moving parts and vertical takeoff and landing. We plan to incorporate some xenon experiments into this device. If they work out as well as we're hoping, the xenon gas on board a device like this will allow us to drastically increase the thrust during takeoff and landing. That's really an important thing because takeoff and landing is sort of our weak link in the chain. That's where we need the most thrust to get off the ground. Once we're airborne horizontally, we've got plenty of lift from the airfoil itself to keep it in the air. Now, when this device flies, it'll be capable of aerodynamics that conventional aircraft would never be able to achieve. One of the reasons is because there's no moving parts. We can project or arrange the airflow in a manner that we can design craft for high speed. We can design them for high lifting capacity. So there's really a lot of possibilities with it.
What's your power source?
Power source on this craft, what we hope to do, this will be the first craft that should be umbilical free. According to the numbers and the data that we've looked at so far for these craft, we need to get to a big size, and this 12-foot device should be capable of lifting its own power source. What I have in mind is we'll have a backup battery source on it, and we'll probably use some kind of a small little gas engine that runs a little electric generator, and that'll be a backup, and that'll actually provide power for the craft. Flight times we can't even really talk about at this point because there's so much research that needs to be done yet. This is a picture of the 8-inch model that's hanging from the front of this cardboard box, and you'll see there's nothing to it. It's a window screen that we cut away to form 1/4-inch squares in this grid. We did that for a couple of reasons. Window screen is actually too heavy. It won't produce enough thrust to actually lift it. The other reason is the window screen off the shelf from a window, the wires are too close together. With that close of wire, the ions have a hard time releasing the airflow through those smaller spaces, so the thrust is reduced. Basically, we've got balsa wood struts on all 4 corners, and you can't see it in the picture, but there's an X, there's an emitter wire going from corner to corner.
Do they touch in the middle?
Yeah, they touch, and that's a tricky thing to get on these primitive models. Is I try to stretch the wire so that they can be constantly touching. I think on this model I had problems, so I just tied a small knot with a little piece of the wire. This is a picture of the bigger craft. This is a 12-inch prototype, and we were able to incorporate all the X's, all these little balsa wood struts that you see. You can't see the emitter wires, but there's a number of X's of ion wire in between all these struts. By doing it that way, we were able to get good coverage of the ion spread across the lower grid. Unfortunately, one of my goals with this model was to build a rigid airframe, and it just didn't work that way. Although we get a lot of added thrust from this configuration of X emitter wires, you can see that the increased number of vertical struts adds to the weight, and there is an overall net thrust, but some problems definitely need to be solved in order to increase that further. This is a picture of our 3-foot craft. The structure is actually complete, but we're in the process of incorporating these new emitter configurations into this craft. It looks real promising. The craft is pretty solid and it's pretty light. And this will be the next major step forward. This is another picture of the craft from the side. It's built out of balsa wood and epoxy. Okay, so well, let's take a look at the demonstration. Keep in mind this demonstration is very primitive. Some of you may think, well, you know, what's it? It's not much. It's flexible, but try to have a little bit of vision when you look at this and imagine the possibility of a rigid structure incorporated into this. So let me just go over to the device and show you. The device is hanging from this box here, and we tried to separate the high voltage wires so that so they don't arc in between each other. Now you can see from that demonstration, it's producing more thrust than it weighs, which is a good thing. These sparks are caused by ionization losses in between the wires, and partly because it's flexible, we don't have a rigid structure, so the wires are actually bending and being attracted closer. But it easily hovers, it easily flies. The reason I'm not flying it is I've been shocked far too many times by this. As it flies, it tends to jump right to my hand every time, so I thought the box would be a good idea. This device flies very well, though. It does produce a good amount of thrust because it is so simple. So let me show you the bigger device now. This is the 12-inch model. And I'll just take a minute and wire it up here. And I'm going to use my precision laser engineered plastic fork to keep myself from getting shocked. This is about 20,000 volts DC at about 1 milliamp. And believe me, it doesn't feel very good. Polarity is an interesting issue. Let me just show this real quick and I'll mention that. Lower voltages, we've tried varying the voltage. In fact, we're working on a microprocessor controller for this right now that will allow us to vary the voltage and actually get the craft to hover and level flight. We're still a little ways from that yet. Now this is unfortunately an unstable craft also. It tries to fly wherever it wants to fly. Yeah, that's a good idea. Yeah, it's, like I said, it's flimsy and it's very difficult to contain these wires so that they don't short out. This craft is about 0.3 to 0.4 ounces. It does produce more thrust, but the added weight is a little bit less efficient than the smaller model. But the real trick here is the sizing. It's a pretty significant step forward having a bigger craft. It's real hard to see because I have to hold these wires. The reason I have to do that is the craft has a hard time lifting the weight of its own wires. And obviously, if we could lift the weight of its wires, it would be able to fly to the ceiling and you'd be able to see it much better. With the larger craft, the 3-foot craft, we should easily be able to do that. We should be able to lift the craft from the floor probably 5-6 feet off the ground, and the wires would just dangle below. But that's the basics of it. Like I said, we're in the process of trying to do more research on the technology and improve it. I think there's a lot of potential here with it, and I think it can be taken a lot further. The point of polarity on this craft is an interesting one too. We've tried it both ways. The textbooks say using a negative emitter on the top is 5% more efficient. I have yet to see it really. So right now we're using a positive polarity on top. And if anybody has any questions, go ahead.
The person was studying that device was high voltage, and he got sick, and he got because of
Well, the device actually produces negative ions. It produces ions, well, depending on the polarity that we're using. It produces ion thrust out the bottom of the craft. And other than a lot of shocks and a little bit of breathing of ozone gas, it creates ozone gas because of the high voltage arcing. I've been working on this thing for a number of years, and I haven't experienced anything. I don't think the health aspects are really a concern to me right now.
You ever thought of, I guess, aluminum extrusion would be, for a frame would not work because it would short it out.
Yeah, one of the things we're working on right now is trying to come up with a better design for the lower grid. The lower grid is really one of the most important things with the craft. The trick is we've got to try to get about a 1/4 inch spacing, and we've got to try to use light wire. Well, you could probably try to imagine what it would entail cutting out a piece of window screen, just a 12-inch piece. Just to give you an idea, I started cutting that in November, and I finished it in June. I mean, it's a little bit confusing, but we're basically cutting every other wire on this piece of window screen, vertically and horizontally, and it allows us to open up these spaces into bigger holes. So one of the things we're working on is to try and get this wire weaved, or actually woven, and you know, it's not cheap. They've got to set up machines to specially weave it, and it's such small diameter wire that it tends to be real flimsy. And until we get a little bit more concrete research done with it, I'm reluctant to spend too much money on it.
What about chicken wire?
I've tried chicken wire. It's too heavy, and the spacing is too wide. We need it ideally with about a 1/4 inch to a 1/2 inch spacing. Now, you can actually string those wires yourselves, but at those wire sizes, it's just so time consuming, and it's so difficult because if you've got a broken wire, sometimes it affects so many other wires next to it. It's just a complete nightmare. And that's actually how I started out with this craft. I used to string the wires manually. Go ahead.
For practicality reasons and purposes, why not go ahead and make this unit in modular configurations and use it for the replacement of the blower and heating and air conditioning system?
The reason basically that it's not used for that is it doesn't really create much thrust. It creates small amounts of airflow. To be able to produce the amount of airflow that a blower or a fan would produce would require a device so big that it really wouldn't be practical. The airflow is there, but it is small. When you've got a light weight, however, it's enough to lift the craft.
What about curling it over, making it tubular, where your cross wire could be support, and you'd only have 2 wobble ends to deal with instead of 4?
Yeah, that's something that I have looked at. One of the major goals that I think is very important with this technology is to try and recreate some of these experiments that D. Seversky has done. And you know, to be honest, some of the stuff he did is very difficult to duplicate. He had a substantial amount of money to work with, so he was able to have you know, the craft made exactly the way it should be, and it's just so time-consuming to do. But once we can achieve a rigid structure, that's really the stepping point to this technology to take off, because it's then easy to scale this technology up as big as we want to scale it. And like I mentioned about the efficiency, on a craft 12 or 20 feet in diameter, your efficiency is raised substantially because of the configuration of the wiring. Over there in the back.
Have you tried something other than wire, perhaps a plated fabric fiber?
Very good question. I've tried carbon fiber strands, but to try and find carbon fiber at 2.5 mils, I haven't been able to find it. I have tried larger pieces of it.
I mean cloth, not sewing
I haven't tried that, but I have a feeling that it will result in a lot of losses. It'll probably tend to prevent the dispersal of the ion flow to the lower grid, but that's not a bad idea to try.
What about silk?
I haven't tried silk, but I really think that the key is the wires. I think it's the configuration of the wires that is really the key to the technology. You know, if you think about it, one of the simplest improvements that we made recently, if you imagine that device with the X piece of wire, on the 3-foot model, what we plan to do is run multiple numbers of parallel wires. So it'll actually be a grid of crisscrossed wires, but it'll just be tilted so that all the wires run on a diagonal. And it's a great idea, but actually building the craft like that and stringing these hair-sized wires 3 feet long is an actual nightmare. That's our next step, actually. I've got a couple different types of wire on order that we'll try out. I think that's going to be the key. The stainless steel wire is nice and strong. It's actually hard to break. It's so strong. But it's a nightmare to work with. Yep. And that's really going to be, I think, when we start making some leaps forward is when we can find solutions to a lot of these simple problems and be able to make it easier to produce and easier to build.
One of the findings of this machine, the direction of this flying is controlled by not magnetic, some polarity cosmically ray, one from a Sirius and the other side, which is that the direction of this flying is controlled by some kind of energy flow from a Sirius.
I'm not really familiar with that. Control of the craft is really easy to do. However, you can tilt the craft and bank the craft real easy just by sectioning off parts of the lower grid into 4 different sections. Now you've got 4 different banks. By energizing each bank, you can cause the craft to tilt or roll or basically move in any direction. Really, you could build the craft in any shape or size that you wanted. You could build it in any type of configuration as long as it's composed of these stacked grids.
Would you need separate power supplies for this control? I don't see how you would do it with one.
Well, we're actually working on a pretty revolutionary power supply that's a completely solid-state high-voltage power supply, 20,000 volts DC. And there's I don't want to talk too much about it. It's another gentleman's invention, but I think it's going to work out well. It'll allow us to much cheaper and more effectively produce these high voltages, and that's what we basically plan to use on the larger craft, the 12-foot craft. Most of the less sectioning off of the grids that you can do, the better, because it just complicates things. Really, stability is the key, but you also want to keep it simple.
Suggestion for you on your frame, make an inflatable inner tube and a small tube for your spacing, and string your wires across the tube at the lower grade front grid, and the helium help with the
Yeah, I'm not sure about the ion flow between that, but it's an interesting idea. I think our next, some of our next experiments are going to be the injection of xenon gas into this craft, because that'll be real interesting to see if it affects our output thrust at all. And if it does, then it'll really greatly add to the thrust. Anybody else have any questions? Go ahead.
I have seen Alexander University movies that were done and then later duplicated on VHS, and it does work. It's not isn't science fiction. And I'm sure you've seen it.
Yep, I
Straight up, you can go all the way up to the ceiling, hover, you can adjust it, tilt it at any angle. So it's definitely a viable science.
absolutely, and I have seen the video personally, and it does fly from floor to ceiling, and it lifts. He's got 5 or 6 wires strung up to it, because he actually can tilt and bank the craft. Unfortunately, there's a lot of things in his craft that he never disclosed in his patents or publicly. So a lot of this is having to reinvent the wheel, unfortunately. Okay, if there's no other questions, just want to mention, oh, go ahead.
Well, this is just, it's something that I got a schematic for you on your radio connection. Putting out 9 watts, 36 volts. I just want to say I strung a 12-gauge wire from the top of my house to an oak tree, 350 feet. I got 36 volts, but only 1/100 of a watt. Can you tell me why I didn't get 9 watts?
Sure. A lot of this technology that we deal with is some real revolutionary stuff. And like I said, we try to verify as much of it as we possibly can and get it to actually work the way many of the inventors say it works. Stuff like these free energy devices, you know, everybody's been chasing that technology for forever. And you know, there's a number of people that say that they're close, and I've been hearing that for 15 years. So you know, we sell a little power module that produces its own energy off of ambient radio waves, but it varies so much between your locations and you know, how much RF is in the air, so it's real unpredictable. But we do sell, we've got all the plans for these devices. The Ionocraft is in our catalog. We sell plans for it. We try to update it constantly. There's always new breakthroughs, and so we always incorporate them into the plans. But those plans can be ordered from our catalog. There's a phone number on there and everything. And they contain copies of the patents and some more information that I didn't go over. And I guess that's about it. Anybody that's interested in this, go ahead.
One question, how would you disperse the xenon gas?
Well, from what I understand, NASA used some nozzles to actually inject the gas into the chamber. In a larger craft, in a small craft, it should be easy to just possibly spray the gas down into it. But in a larger craft, you need some kind of ejection manifold to inject this gas into the grid area. Yeah, basically, you know, it's producing thrust, and it actually sucks air from above it, and so it'll actually suck that air down and thrust it out the bottom. So I'm real interested to see, like I said, what will happen when we spray some xenon gas onto this thing as it flies.
How can you get it up to over 100,000 feet in flight?
That's a good question. You know, this craft will be subject to the same problems of fixed-wing aircraft in high-altitude flight. However, carrying a bottle of xenon gas, it's now able to basically flies, you know, past the thin atmosphere that conventional aircraft wouldn't be able to.
One of the problems in high altitude would be that if you want to maintain the power level at 20,000 volts, you would have to increase the distance between the emitter grid.
Yeah, in fact, that's another area that you know, volumes of text could be written on, and unfortunately, it's just time-consuming work. That's one of the areas that we really need to go into is testing some different separation distances. I have experimented with it to some extent, and that's why I've stuck with the 1 3/4. It just tends to work best for some reason.
How do you plan on overcoming the weight of power supply?
Really, as the craft becomes bigger, it becomes more efficient, and we're able to get better density of these emitter wires in the craft. So, yeah, we can remove the tether. If you can imagine, like the small craft here that was 8 inches, you know, we've got a net thrust of 0.1 ounces. If we had 1,000 craft that size linked together without any additional weight, we've got a pretty significant amount of net thrust. So it allows us, really, the size is the trick here. We need to build it big enough so that we can get enough net thrust to lift these components on board it.
One more question. If you had high enough altitude, would you still have the ozone generation, the byproduct of the ionization? And if so, would you make several of these modules linked together to help fill the hole in the ozone layer?
That's an interesting idea, but from my understanding, the ozone is produced because of the atmosphere that we're producing the arc in. So I'm not sure about xenon. I'm not sure if ozone gas is produced with a high voltage arc in xenon or not, but to my knowledge, in space or in a vacuum, it wouldn't be produced. Okay, I guess that wraps it up. Anybody interested in this technology, feel free to talk to me. I'll be around here in and out today.